We are living in a world where AI can already help with many different problems, from answering simple questions like what is 1 plus 1 to explaining complex ideas, writing code, and even providing directions for real-world situations. But recently, we have started moving towards something more ambitious. AI systems that are not limited to only answering questions or giving language-based responses. Instead, these systems can observe an environment, understand a goal, make decisions, and perform actions. For example, imagine an AI that can look at your screen, understand what you are trying to do, open the right application, search for information, write a response, and even correct itself if something goes wrong. This system is often called a Generalist Agent AI, or GAA for short. The word generalist means that this type of system is multi-purpose. It can handle many different tasks across different environments. The word agent means that it does not only produce an answer, it can also take actions. So instead of just asking what should the answer be, we start asking what should the AI do next. But how did we get here? The year was 1913, long before TGBT. A Russian mathematician named Andrei Markov was studying something familiar: text. But he was not reading text the way we usually do. He wasn't asking, what does this poem mean? Instead, he was asking a more mathematical question. If I know the previous symbol, can I predict what kind of symbol comes next? Let's start with a simple game. Let's say we have an incomplete sentence. The capital of France is. Of course, most of us already know the answer is Paris, but what if we had no prior knowledge? What if we were only allowed to look at a huge collection of text and learn from patterns? Think of it like being thrown into a library and asked to read every book you can find. Luckily, after reading enough text, you slowly notice that the phrase "the capital of France" is most likely followed by the word Paris, so instead of answering from memory, you answer purely based on statistics. With that idea in mind, language models, or LLM, are built around a similar mechanism and can be formulated using the equation P of W given H, indicating the probability of the next word, W given the context, H. Following that, the model produces a probability distribution, and then a decoding step decides whether to pick the highest probability word or to sample from the distribution. Ideally, Paris receives the highest probability, while unrelated words like banana receive a very low probability. So the model is not directly saying I know geographic, rather it is saying based on the patterns I learned from data, Paris is the most likely continuation. Let's return to the formula. In general, the more useful context the model has, the better its prediction can become. Think about it. If the only context we had was a Francis, we would not know whether the sentence was talking about the cuisine, the capital, the flag, or something else entirely. But if the context is "the capital of France is," the answer becomes much clearer, so at first the solution seems obvious. Just give the model more context, but this creates a problem. In other words, better context leads to better prediction, but also longer context leads to higher computational cost. Now we know that context matters, so naturally we might ask how much previous context should the model look at. The earliest language models answer this question in the most direct way possible. They looked at a fixed number of previous words and counted how often certain word patterns appeared in text. In this case, UN represents the number of words, which means the context will be n-1 words long. UN is usually ranges from 1 to 6, and these models are named according to their value of n, a unigram for n as 1, a bigram for n as 2. You get the idea. The main problem is that n-gram models do not scale well. For example, if the vocab size is 50,000, then a bigram model can have 50,000 squared equal to 2.5 billion possible word pairs. You get the idea, so even though increasing n gives the model more context, the number of possible word patterns grow exponentially. This creates two major problems. First, the model needs a huge amount of storage to keep track of all these possible combinations. Second, many combinations may never appear in the training data, and this is called data sparsity. If language is full of repeated patterns, then the simplest possible strategy is to count those patterns. Count how often the capital of France is Paris appears, and count how often the capital of France is London appears. Then use those counts to decide which continuation is more likely. It is simple, intuitive, and almost brute force. So instead of asking the model to store every possible word combination in a giant table, we ask a new question. Can the model read words one by one and compress the context into a learned representation? This brings us to RNN. Instead of remembering language as a table of word counts, and RNN remembers language as a hidden state, a learned vector that gets updated each time the model reads a new word. The context of a language model is now compressed into a fixed-size vector. This process is called tokenization. Tokenization helps the model represent language using smaller reusable building blocks instead of creating every possible word as a completely separate object. But that is a story for another time. Let's not get too far from our main topic. You can think of RNNs as standard neural networks with a dimension of time added. As each token is read, the model updates its memory, shifting from memorizing word patterns to learning a compressed representation of context. In a way, this makes RNNs feel a bit more human. When we read a sentence, we do not store every exact word combination in a giant lookup table. Instead, we keep a rough mental summary of what has happened so far. But there is a catch. Just like humans, these models can forget. And in RNN, this forgetting becomes a serious problem when the sequence gets long. Over time, important details from the beginning of the sentence can slowly fade away. By changing the size of the hidden state, we are adjusting the model's memory capacity. But here's the problem: this memory is still fixed in size. No matter how long the sentence becomes, the RNN still has to squeeze everything it has read into the same hidden state. For short sequences, this works fairly well. But as the sequence grows longer, maybe tens of tokens, the model starts to struggle. Researchers tried to address this problem by introducing LSTM, a variant of RNN with a more controlled memory system. LSTM uses gates to decide what information should be remembered, what should be forgotten, and what should be passed forward. But even then, the fundamental limitations remains. Context still has to flow through the sequence step by step. Information from the first token has to travel through the second and the third and then the fourth and so on before it can affect the final prediction. What if the model did not have to carry memory step by step? This idea brings us to transformers. This also brings us to the present day, where most modern language models are built around attention-based architectures. Take this sentence as his example. The animal didn't cross the street because it was too tired. To understand the word "it," the model needs to know what it refers to. Is it animal or is it street? In older sequence models like RNNs and LSTM, if the relevant word appeared much earlier in the sentence, the connection would become weak. Transformers, on the other, handled this differently. With attention, the token it can directly look back at the previous tokens and assign more weight to the token animal. This is why attention is so powerful. It allows the model to identify which parts of the context matter most for the current prediction. This is also why most mainstream models use this specific mechanism. But attention isn't magic. One issue is called attention delusion. Imagine you have a small bag of candies, but there are too many people asking for them. The more people there are, the harder it becomes to give enough to the one person who actually needs them. Attention can face a similar problem. When the context is short, the model only has a few tokens to focus on. But when the context becomes extremely long, the model has to distribute its attention across many more tokens. So long context still introduces to major challenges. Computational cost, because attention grows roughly within square, and retrieval quality, because the model still has to find the right information among many tokens. After all, a small transformer is just a small model. In fact, modern frontier models are massive. The real surprise was that when researchers made these models larger, trained them on more data, and gave them more compute, their performance did not improve randomly. This is where the scaling laws comes in. Their formulation can be simply described as follows. Wherein is model size, D is data set size, and C is compute. The main intuition is simple. Larger models trained on more data with more compute tend to achieve lower costs. Given how ambitious humans are, we rarely stop at the first successful idea. And naturally, once language models become powerful enough, we started asking, can we go beyond text? This is where the idea of multimodal modules first emerged. Instead of using a single tokenizer for text, the model uses different tokenizers for different types of data. You can think of it like how humans process the word. When we see a dog, our brain does not only see pixels. It connects the visual information with the concept dog. The important point is not that images become text immediately. The important point is that different forms of data can be translated into representations that the same model can reason over. The same idea extends to action-based model, same intuition, different type of data. At this point, it is tempting to think of these models as machines that simply answer questions. You give it a sentence, it gives back a sentence. You give it an image, it gives back a description. In every case, the model takes some sort of input, turns it into internal representation, and then chooses what should come next. For a language model, that is usually the next token. For a multimodal model, it might be the next word about an image, or the next description of a sound, or the next frame of a video. But now imagine that what we ask it to predict is not a word but an action. And this is where the idea of an AI assistant starts to change. A chatbot is mainly trying to answer the question, what should I say next? But an agent is trying to answer a more general question, what should I do next? That small change is the bridge from conversational AI assistants to language-based AI agents, and eventually to large action models, or LLM. Agents generally fall into three main categories. A work agent is useful when the environment is related to productivity. A personal agent is useful when the environment is connected to daily life. A creative agent is fairly straightforward. It is typically used when the goal is to generate something new. These roles are not really distinguished by what the model is, but by where it is used and what kind of task it is expected to complete. And as language models become larger and more capable, they gradually become better at following instructions. One simple way to observe this progress is by looking at how the number of parameters in large language models has grown over the years. As you can see, it all started with relatively small models. And notice that I used the word small even though they were still considered large language models at the time. Models moved from millions of parameters to billions and to hundreds of billions. Alongside these large models, we also see the rise of smaller language models, or SLM. As I mentioned earlier, a chatbot usually follows a simple pattern. The user asks something, the model generates a response, and the interaction ends there. But an agent follows a more active structure. What makes these systems special is that they can interact with an environment such as a document, a calendar, an email box, a database, a browser, or a software interface. The agent performs an action in that environment, then observes the result, and based on that observation, it can decide whether the task is complete or whether it needs to take another action. So instead of single question and answer interaction, we now have a loop: act, observed, reason, and act again. Of course, like other types of models, this loop requires an evaluation process. For a standard language model, we might only care about whether the generated text is correct or fluent. But for an agent, the final answer is only one part of the story. Because of this, there is no single universal metric that can evaluate every agent. Instead, we use dedicated benchmark environments to test specific abilities. For example, Hotpot QA is commonly used to test multi-hop reasoning, where the model has to connect information from multiple sources. WebShop simulates an e-commerce environment where an agent receives a user request and has to search, compare, and choose the right product. ToolBench focuses on tool use, testing whether an agent can select and call the right tools or API to complete a task. As WEave's bench is one of the most well-known benchmarks for software engineering agents, where the agent has to solve real issues from real code's repositories. Those are just some of the most popular ones, but you get the idea. The key point is that different benchmarks test different aspects of agent behaviors. So, how should we design the architecture of the agent itself? After all, not every agent is built on in the same way. We can think of agents' architectures as a spectrum. On one side, we have very simple agents where most of the behavior is controlled by a fixed prompt. On the other side, we have more complex systems where the agent can learn from experience, generate actions directly, and even collaborate with other specialized agents. The simplest form is a prompt template agent. Here we do not retrain the model. Instead, we give the language model a carefully written prompt. It is called a system prompt. This prompt tells the model its role, the task it needs to solve, what observations it will receive, and what output format it should follow. A more structured example is React. Instead of asking the model for an answer, React guides the model through a repeated pattern. Reason, act, observe, and then reason again. This makes the agent more suitable for tasks where it has to interact with tools or environments step by step. But if the agent fails, it does not naturally learn from that mistake, and it may repeat the same kind of error later. This leads us to the next type. Learnable prompt agent. In this architecture, the agent can look back at what happened during previous tasks, generate a reflection, store useful lessons, and use them to improve future prompts. So instead of treating every task as completely new, the agent starts to build a kind of memory from experience. But we can go one step further. Instead of only improving the prompt, we can train the model directly on agent behavior. This is the idea behind large action models. A standard language model is trained to predict the next text token, but a large action model is trained or fine-tuned on agent trajectories. That means that it learns from examples of given a task and observation what action should be taken next. And finally, for tasks that are too complex for a single agent, we can use multi-agent orchestration. Instead of asking one agent to do everything, we divide the work across multiple specialized agents. One agent might be good at planning, another at searching, another at coding, and another at reviewing the result. Then a controller decides which agent should act at each step. This makes the system more powerful, but also more complicated. It can become slower, more expensive, and harder to debug, and the whole system depends heavily on whether the controller chooses the right agent at the right time. So overall, agent architectures move from simple prompting to learning from experience to action-trained models and finally to systems of multiple cooperating agents. Now we begin with the idea of generalist multimodal models, models that can connect vision, language, and reasoning in a single system. For a long time, computer vision was organized around separate tasks. One model classified images, another detected objects, another estimated poses, segmented regions, predicted 3D structure, or estimated surface normals. Deep learning pushed this field forward very quickly. The research curve grew sharply, with thousands of papers submitted and accepted. This shows how much progress computer vision made during the deep learning era. But there was also a limitation. Traditional computer vision often relied on specialist models. Each model solved one narrow problem. Image classification needed one dedicated model. Object detection needed another. Semantic segmentation needed another. As a result, foundation models emerged as a powerful paradigm in AI. Instead of building a separate model for each task, a single foundation model can be adapted to perform a wide range of tasks such as question answering, sentiment analysis, information extraction, image captioning, object recognition, and instruction following. The next step is large generalist multimodal models. These models combine language and vision. They can understand visual data and communicate naturally in human language. The central challenge is training them efficiently. How can we build strong multimodal models with only a limited amount of supervised data? The strategy is to reuse pre-trained foundation models, then fine-tune them with carefully designed semi-automatic data collection methods. That is the key transition from many separate specialist models to one more flexible multimodal model. Now let us look at the basic architecture of a generalist multimodal model. The input begins with an image. A visual encoder extracts image features and turns the image into a visual embedding. But a language model cannot directly use raw visual features. So the model needs a cross-modal connector. This connector maps the visual embedding into a language-ready representation. After that, the language decoder can combine the image representation with a text instruction. To train this system, we usually need two stages. The first stage is self-supervised pre-training, where the model learns general representations from large-scale data. The second stage is instruction tuning. This is where the model learns how to follow user requests and produce useful answers. Instruction tuning requires instruction data. So the question becomes, how do we create enough high-quality instruction tuning data? One option is to use humans. Human-written examples can be high quality, but they are expensive and slow to collect. Another option is to use machines. A strong language model, such as GPT, can act as a teacher and generate many examples at scale. For text-only data, this is simple. We give GPT a prompt and ask it to produce an output. For multimodal data, the problem is harder. We need image, instruction, and output examples, but GPT only accepts text. It cannot directly see the image. The solution is to convert the image into context information. For example, we can describe the image with a caption and lay out information, such as objects and bounding boxes. Then we prepare a few manual seed examples. These examples show GPT the format, context, instruction, and output. Once GPT understands the format, it can generate many training examples. These examples include conversations, detailed descriptions, and complex reasoning questions. The result is Lava Instruct 158K, a large visual instruction dataset used to train a multimodal model to follow image-based instructions. Now we focus on Lava and how a language model can learn to see an image. Lava consists of three key parts: a clip vision encoder, a projection module, and a large language model. The image is first encoded into visual features by clip. Then, a trainable projector maps these features into the language model's embedding space. After that, the projected visual tokens are combined with the user instruction and sent into the LLM. Based on both the image and the text prompt, the model generates the final answers. The vision encoder turns the image into visual features. We can describe picture as vector ZV equals 2 g theta of xv. In simple terms, the image becomes a sequence of feature vectors. However, these visual features are not automatically compatible with a language model. Language models work with token embeddings, not raw image features. This is why Lava uses a projector. The projector learns a bridge between the visual feature space and the language embedding space. To bridge this gap, Lava introduces a trainable projector. The projector transforms the visual representation ZV into a new representation HV that is compatible with the language model's embeddings. In the original Lava, this transformation is performed using a linear projection HV equals W of ZV, whereas Lava 1.5 adopts a two-layer MLP for a more expressive mapping. At the same time, the user's instruction is tokenized and embedded through the language model's embedding layer. For example, a question such as "What is unusual about this image?" is converted into a sequence of language embeddings HQ equal to embeddings of XQ. Then the model combines visual embeddings and question embeddings. Together, they become the context for the LLM. The LLM generates the answer token by token. It predicts one token, then uses that token as part of the context to predict the next one. This is the same autoregressive process used in text-only language models, but now the context also includes visual information. Training happens in stage. In stage 1, Lava learns alignment. It uses image caption data such as a CC3M subset. During this stage, the vision encoder and LLM stay frozen and only the projector is updated. This teaches the projector how to translate visual features into the language model's embedding space. In stage 2, the model learns visual instruction following. It uses instruction data such as Lava Instruct 158K with image, instruction, and output examples. Only projector and LLM are updated. Now the model learns how to answer visual questions, follow instructions, and produce helpful language responses. The key insight is that Lava does not train everything from scratch. It reuses a strong vision encoder, reuses an existing LLM, and learns the bridge between them. After training, Lava can do more than simple object recognition. It can answer open-ended questions about images. For example, consider the question, "What is unusual about this image?" Other models, such as GPT-based vision systems, Blip-2 or OpenFlamingo, might primarily describe the visible objects in the scene, mentioning a person and a vehicle without fully explaining the situation. However, Lava goes further. It recognizes that the person is sitting on the back of a moving minivan, understands that this behavior is unusual and potentially unsafe, and explains why maintaining balance in such a situation can be difficult. Lava can also interpret images that require background knowledge. In the Mona Lisa example, the model needs to recognize the reference to the painting and understand that the image is a parody. That means the model is combining visual perception with cultural knowledge and language reasoning. Another important ability is combinatorial task generalization. The model can combine skills that were learned separately. It may recognize multilingual, visual conservation, OCR, and improve writing. This is powerful because the model is not only memorizing training examples. It can compose abilities to handle new combinations of tasks. Lava also shows multilingual generalization. If the image is given with a request to answer in Chinese, the model must combine vision, language, and multilingual generation. So the model is not just mapping images to English captions. It can adapt its response to the user's instruction. These examples are useful, but qualitative examples are not enough. We also need quantitative benchmarks. In the benchmark table, Lava 1.6-3 for B performs strongly against other models on multiple datasets, including MMMU, MathVista, and MMBench. The radar chart gives another perspective. A larger area means the model has more balanced capability across different benchmarks. The main takeaway is that Lava is not only a demonstration system. It is a general visual language model that can be evaluated across both qualitative examples and quantitative benchmarks. Standard Lava can understand images, but users often want to ask about one specific region. For example, instead of asking, "What is happening in this image?" we may want to ask, "What is the person pointed to by the arrow doing?" This is where visual prompts become important. Earlier region understanding methods often felt unnatural. They required users to describe a region using bounding box coordinates, region tokens, or learned position embeddings. That works for machines, but it is not how humans naturally communicate. Humans point, circle, draw arrows, scribble, or highlight the part they care about. VIP Lava is designed around that idea. Instead of forcing users to speak in the machine's format, it lets users draw directly on the image. The original image and the visual prompt are blended together. The result is a marked image. The model receives both the image content and the user's spatial instruction. In the architecture, instead of processing a plain image, the model receives a marked image where a specific region is highlighted to indicate the user's area of interest. This visual cue allows the model to focus on the relevant part of the image before reasoning begins. The marked image is first encoded by the clip image encoder, producing a visual feature representation ZV. These features are then passed through a fusion projector, which consists of layer normalization and MLP layers. The projector integrates information from both the original image content and the visual prompt, generating a set of visual tokens HV. Next, the visual tokens are combined with the user's text question and fed into the large language model. Because the model already knows which region is important, it can perform more accurate reasoning about the highlighted area. The model uses a fusion and projection module. This includes layer normalization and an MLP. Layer normalization first stabilizes the feature representations, making them more consistent and easier to process. The MLP then learns a transformation from the visual feature space into the language model's embedding space. As a result, the image features are converted into visual tokens that can be seamlessly combined with text and understood by the LLM for reasoning and answer generation. VIP Lava supports many visual prompt types. These include mask contours, ellipses, bounding boxes, triangles, scribbles, points, arrows, and filled masks. This flexibility matters because different users may mark images in different ways. The model should understand the intention behind the mark. With the same image and the same text question, changing the prompt can change the correct answer. If the arrow points to one object, the model should describe that object. If the arrow points somewhere else, the answer should shift accordingly. This makes visual prompting more natural than coordinates and more specific than whole image captions. The central idea is simple. Users can communicate with the model by drawing directly on the image. This example will highlight the key idea of VIP Lava. The image and the question remain exactly the same, but the visual prompt changes. In the left example, the arrow points to the skier in blue, so the model describes the person in blue. In the right example, the arrow points to the skier in white, and the answer changes accordingly. Finally, we look at evaluation, future directions, and the broader conclusion. VIP Lava is evaluated across many capabilities: recognition, counting, captioning, visual reasoning, OCR, and math. Across multiple task groups, the model achieves strong results. It performs well on object recognition, object counting, visual reasoning, and region captioning. But scores alone do not tell the whole story. We also need to understand what kinds of questions the model can answer. The Visual Prompt Understanding Benchmark contains complex questions. A single question may require perception, OCR, world knowledge, mathematical comparison, relation reasoning, and language generation. In the vegetable example, the model must look at the correct region, read the price table, compare the prices, and identify the answer. This is not just object recognition, it is a chain of visual and language reasoning steps. Yolava explores personalization. Instead of recognizing only a generic person, the model can learn a specific identity, such as Maya. This moves the model from generic recognition toward personalized multimodal understanding. Matryoshka multimodal models introduce another direction: adjustable granularity. A coarse representation uses fewer tokens, gives a broad view, and can run faster. A fine representation uses more tokens and preserves detail for harder questions. Even with strong results, the problem is not solved. Models can still hallucinate. Video understanding remains difficult. Smaller models need to become more capable. OCR behavior is still not fully understood. And instruction tuning can shift the model's knowledge in complex ways. Looking ahead, multimodal models are evolving beyond image question answering. They are becoming AI agents that can observe, reason, plan, and interact with external tools. At the same time, visual prompting is being extended to robotics, where highlighted regions can guide actions in the physical world. These developments move multimodal AI closer to real-world decision-making and interaction. A multimodal AI agent follows a simple cycle: perceive, reason, and act. It gathers information from multiple modalities, uses memory and reasoning to make decisions, then takes actions through text, tools, or robots while continuously learning from environmental feedback. For example, an agent may observe the sky, call a weather API, infer that it may rain, and decide that a robot should bring an umbrella. Robot learning is another future direction. Visual prompts can guide actions in physical space. Visual cues are no longer used just for understanding images, they directly guide physical actions such as picking up objects, avoiding obstacles, and sorting items correctly. In conclusion, we are moving from specialized models to general, multimodal models. Platform models, semi-automated data generation, visual suggestion, agent models, and robotic machine learning all aim for controllable visual understanding. The goal is to build systems that can see, reason, follow instructions, and ultimately act in the real world. We'll explore how robots can learn new skills simply by observing demonstrations. Two scenes, different geometry, different robot body, but the same intended relation. B rests on A. The question for generalization is not whether the motions look alike, but whether the goal relation is preserved. Defining generalization this way immediately separates task identity from visual similarity. A demonstrated trajectory encodes the task, but it also encodes the geometry of that specific execution. When the environment changes, the trajectory replays every incidental constraint, the starting pose, the clearances, the exact object placement. The path that succeeded before now collides. This is the fundamental gap. A trajectory is a sample from the task, not a description of it. If a trajectory is an execution sample, what would a description look like? The answer is a precondition and a postcondition, a mapping from one state to another, T, ST2, ST plus 1. The world geometry that caused the trajectory to fail is not mentioned. Only the relational change that the task must produce is specified. This is the core abstraction. A task is defined by what must change in the world, not by how the agent moves through it. But a state transition requires a state representation, and the representation determines which differences the task ignores. For part assembly, the relevant state is the contact relation between faces. For knot tying, it is the topological class of the string. For legged locomotion, it is body pose and foot contact. The same abstract transition ST to ST plus 1 takes a different concrete form in each domain. Choosing a representation is therefore a modeling commitment. It decides what the task sees and what it is blind to. Given a contact state representation, not all 49 conceivable transitions between 7 states are physically realizable. Kuhn-Tucker analysis of the surface constraint geometry reduces this to roughly 20 possible transitions. Of those, only a subset appears frequently enough in manipulation data to be worth implementing. Bring, pick, place, drawer adjust, drawer open, drawer close. These are not motion clips, they are generators of specific contact state transitions. The skill library is derived from the transition graph, not defined arbitrarily. Observation now has a clear target. Identify which transition the demonstrator intended and where in the world it should be grounded. A VLM or GPT encoder maps the visual demonstration and any language instruction into exactly to quantities, the requested primitive, and the spatial parameters that locate it. Everything else in the observation, the joint trajectory, the specific hand path, the timing, is deliberately discarded. The task model M equals what, where is a lossy compression, but the loss is intentional. The task model M is an interface, not a motor program. It specifies which transition to produce and where, but it says nothing about joint angles, end effector paths, or timing. That information is not passed across the boundary. On the other side sits a skill agent, a controller that already knows how to produce one specific contact state transition for one class of embodiment. The factorization works because the task model side is invariant to embodiment, while the skill agent side is specialized to it. The necessity of local feedback control follows from a simple observation: the environment reacts. For gesture or navigation, reaction is low and a symbolic plan suffices. For manipulation and locomotion, contact forces, slippage, and object compliance produce disturbances that cannot be fully anticipated at planning time. As environmental reaction increases along this spectrum, the fraction of the task that must be resolved online inside a closed-loop controller grows correspondingly. Symbolic task encoding cannot absorb what only real-time sensing can resolve. Inside the skill agent, the symbolic goal G is held fixed while action is computed as AT equal to PK of XT, G, and theta, a closed-loop policy conditioned on current state, goal parameters, and agent-specific weights. Vision and force feedback enter through X_T, allowing the agent to react to contact variation, object pose uncertainty, and mechanical compliance in real time. Embodiment differences, link lengths, joint limits, actuator dynamics are absorbed into theta. The task specification remains untouched above the interface throughout execution. Two robot bodies receive the same task model. They produce different joint trajectories, different end effector paths, different timing profiles. Yet both arrive at the same contact state post condition. This is not a coincidence, it is the predicted consequence of the factorization. If the task specification is invariant to embodiment and the skill agent handles embodiment internally, then motion diversity is not a failure of consistency. It is evidence that the interface is doing its job. Transfer is not guaranteed by the architecture alone. Three conditions must hold simultaneously. The state representation must capture the task-relevant distinctions are: the grounding of task model parameters into the observed scene must be correct G, and the required skill transition must exist in the agent library K. Failure of any single condition breaks the chain. Modularity makes these failure modes independent and diagnosable, but it does not eliminate them. Learning from observation is a factorization problem. Observation yields a task model, an invariant specification of which state transition to produce and where. Skill agents decode that specification into embodiment-specific action under closed-loop control. The invariant layer transfers across geometry and hardware. The adaptive layer absorbs what changes. Neither suffices without the other. Invariant specification without adaptive execution is not deployable. Adaptive execution without invariant specification does not generalize. The factorization is the method.